Hello everyone, once again you're welcome to this channel. Today we have a peculiar question on how to calculate the natural frequency of a rocker arm of a combustion engine. Once again, how to calculate the natural frequency of a rocker arm combustion engine. Now, today we have a schematic diagram of a rocker arm rotating at 0 point with a cam moving it upward in this direction while the spring is going down on the rocker arm point, and the valve of the mass is entering down as a mass via a damping viscous oil given here, and the length of the rotation from the rocker arm to the pivot is L. Now let's pull out all our parameters. We're given the rocker arm moment of inertia to be 0.35 kilogram per meter cube. We're given the length of the pivot to the rocker arm spring to be 0.20 meter. We're given the mass of the valve going down, the viscous oil, to be 0.15 kilogram. We're given the spring stiffness to be 150 Newton per meter. And we're given the viscous constant of the oil where the valve is going down to be 0.75 Newton seconds per meter. Now, how do we calculate the natural frequency of this dynamics system? By using the schematic given over here, we can deduce that as the rocker arm is going down the viscous oil with the valve entering, there's a displacement of x which equals to L theta, with the reference length of L given here from the pivot to the rocker arm. Now, by deducing the static schematic, we know quite well that the reaction of both the viscous and the spring is going upward, that is CS dot plus KS is going up, while the rocker arm rotates with an angle. So therefore we can juxtapose the static schematic to the dynamics, telling us that as the Mx is going down, Ms dot dot is going down, there will be J theta dot dot rotation. Now, by equating the dynamics and the static equation together, we have summation of moment about 0, that is about the pivot, equals J multiplied by theta dot dot plus ml dot dot L equals minus kxl minus cx dot L. And know fully well that x equals L theta and x dot equals L theta dot and x dot dot equals L theta dot dot. Then we can substitute this value into the previous equation, and that gives us this equation. And by this, we can juxtapose the final derivation of equation with the normal standard mass dynamics equation, which is ms dot dot plus cs dot plus ks equals 0. Now, from this particular equation, By linearizing them together, we can find the mass to be J plus ml squared, and our C, which is a viscous constant, equals CL squared, and K, that is the stiffness, equals KL squared. Now, by inputting all these values into the formula for natural frequency, which is Wn equals K over M, that gives us KL squared J plus ml squared, all into square root. Therefore, our Wn becomes 4.11 radian per second. From there, we can find our natural frequency in Hertz by using the formula of Wn equals 2 pi f. So therefore, our f in Hertz, that is the frequency in Hertz, becomes Wn over 2 pi, and that gives us 4.11 over 2 times 3.14. That gives us 0.65. So therefore, the natural frequency in Hertz for the Rockingham system of internal combustion engine becomes 0.65 Hertz. Thank you.